Hi, my name is Marco. I'm a researcher at Microsoft Research. I'll be presenting this paper that we had at ACL this year. This is joint work with folks at the University of Washington and Samir, who is at the University of California, Irvine. And it's called Beyond Accuracy, Behavioral Testing of NLP Models with CheckList. So this is the question that we're addressing in this paper. How do I check if my model works? So let's say that I'm a researcher or an engineer or a data scientist or whatever, and I come up with a model, deep model or whatever. And let's say that my model is really good on benchmarks. So I go ahead and write a paper saying, like, let's say that I name my model Oscar to keep with the trend. And let's say, look, I wrote this paper, this model is great on all of the benchmarks. How do I know if it actually works? For example, should I go ahead and replace my doctor with Oscar if I beat doctors on a diagnosis benchmark based on text or something? Or if I work at a company, which in my case I do, I work at Microsoft, should I go ahead and use Oscar in all of the products right away because I have good accuracy numbers? And you may be thinking, well, don't you know cross-validation? Like just have a hidden test set and there you go. But there's many problems with accuracy. Like if you've ever trained a model and tried to apply it in the real world, you know that the accuracy you get on the benchmark is almost never the same as what you get in the real world. There's many shortcuts that models can use to do well on test data that don't generalize. So you still want to check, like you want to make sure that it works before you put it into production. So one approach that we as a community have taken, and I have done this myself, is to write more papers. So if I have a paper on Oscar, I write a follow-up paper saying, this is when Oscar works, this is when Oscar doesn't work. Here's in-depth analysis of Oscar. And this is great. This pushes the field forward and helps us build better models. But it doesn't really scale. It seems like a lot of work, and that there's no way that everyone using NLP is going to be going around doing this level of analysis. And you still want to check how your model works. So in this paper, what we're saying is, look, we know how to test software. Let's apply those insights and test NLP models just like we test software. So this doesn't substitute writing the paper. This doesn't substitute other forms of analysis. It complements it. So we're going to try to apply insights from software engineering to testing NLP models. So I have a little color scheme here. Orange is software engineering, blue is NLP, and I'm just going to enunciate a few principles, not all that we use, but a few principles into how we frame them for NLP. So here's a principle from software engineering: test small units. And that, if you think about it, that's the opposite of what we do right now. We have this huge test set, and we treat models as big black boxes, and we have to, basically. You can't go around testing individual functions as you can in software engineering. But we think you still want to test small units. We just changed the definition of what the units are. So in NLP, we're saying let's test linguistic capabilities. So we're guiding people into what to test, and what we call linguistic capabilities is stuff like this. So test the vocabulary of your model. Test if your model can handle named entities, negation. And we have 10 of these as starting points as to what to test. But obviously, these are going to manifest differently in different tasks, and we'll see examples in a sec. So we have linguistic capabilities. Here's a principle from software engineering, from behavioral testing. Tests should be decoupled from implementation. And we know if you are the person who implemented a piece of software and you write a test, you tend to think in the same way as you thought in your implementation. So you tend to write a test that's tailored to the implementation, and that's not a good thing. And again, in machine learning or NLP, this is what we do. We collect a data set and we split it so that the test set has the same problems as whatever is on the training set. It's not decoupled. So we're saying let's decouple tests from training. And the way we're going to test behaviors is with different test types. So there's guidance here into how to test specific behaviors. So we're proposing 3 different test types, and that gives us a matrix where the rows are capabilities and the columns are different test types. So this matrix will guide us into how to test NLP models, and we'll see it in a second. So in software engineering, the most common type of tests that you learn anywhere is unit tests, where you know given certain inputs, what's the expected output? And you use those to test whether software is working. And here we translated that into what we're calling a minimum functionality test. And we call it that because we want to make sure that we're writing not only hard tests, but also easy tests, tests that test the minimum functionality required to understand a certain capability. So for example, let's say we're doing sentiment analysis and we want to test the vocabulary of our model. How would we write a minimum functionality test? We would write examples like these, very simple examples. This was a great flight. I hate this airline. I like the seat. So this is the minimum. At a minimum, if you have a sentiment analysis model, it should have these words in the vocabulary. It should be able to deal with these. Now, maybe we collect 500 of those so we can get a good, if we get a failure rate, we can trust that. So it's not just a couple of examples. Now, if we're testing negation with a minimum functionality test, we would have different examples, different inputs, outputs, and it would be something like this. The cabin crew was not good, the pilot wasn't nice, the flight wasn't great, this, and so on. Like we just basically add very simple negations. And if the model can't handle even this, we would be hard-pressed to say it can handle negation. So this is a minimum functionality test, just like a unit test. In software engineering, we also have this lesser known, but very useful metamorphic tests. And typically they're coupled with property-based testing. What this means is just, you don't know necessarily what the output should be, but we know that if we apply a perturbation, we should expect a certain behavior or a certain property. So here's how we translate this to NLP. One test type is what we call invariance tests. And what this means is very simple. We apply a perturbation to an input such that we expect the prediction to remain the same. Here's an example. If we're testing against sentiment analysis, if we want to know if the model can handle named entities appropriately, one invariance test that we could write is as follows. If you have location names and you change them with other location names, the sentiment should not change for the same tweet or for the same piece of text. Notice that we're not saying what the sentiment should be. So for the first example there, we're not saying it has to get this right. We're just saying whatever the model predicts, if you change Chicago to Dallas, the prediction should remain the same. And that's the behavior we're trying to verify with this invariance test. The last kind of test we have is what we're calling a directional expectation test. And it's the same thing, except that instead of expecting invariance, we're expecting some other property. So for example, if we're testing vocabulary again, we can write a test that does the following. Take an example and add a very negative sentence to the end. So take whatever examples you have and add, I hate you, I dread you, you're lame. And then expect that sentiment does not become more positive. We're not saying it should become negative. We're not saying it has to go down. We're just saying it can become more positive. If you add, I hate you, and stuff becomes more positive, you have a problem. So this is a direction expectation test. Now, checklist in the title is this process. We call it a checklist because you basically go and check individual cells in this matrix. And the process is basically, this matrix gives you guidance. You just fill this matrix and then you test the model. It passes this, it doesn't pass this, and so on. Now, I said at one point that maybe you need to collect 500 examples for a single test. That seems like a lot of work. So we provide a lot of tooling for people to do this at scale. So one way to do it easily at scale is to do templating. So once you come up with a specific example, you generalize into a template. And instead of having to figure out which words to put in, we have Roberta's suggestions. So here's what I mean. Let's say you think of this is a good movie. You can generalize it to this is a positive thing movie. And Roberta will give you a bunch of suggestions that you can pick, great, incredible. And notice that the human is selecting what makes sense in this context. And this helps you generalize quickly to a lot of examples. From one, you create a lot, so you get more coverage. We also have lexicons. So if we're dealing with, for example, if you're dealing with named entities, you're going to need some common names. And we have that for a lot of languages, for like 100 languages or something. We have location names, we have person names, both male and female. And we have a lot of other things that are useful in coming up with tests. We also have a perturbation library, like add typos, add negation, change names, so that it becomes easy, like this reusable perturbations are there. And it also makes it very easy to come up with a new perturbation. Like if you can create a perturbation from one example to another one, testing becomes very easy with this library. We also have visualizations in some. We have a lot of tooling. It's not just a process. We also have a tool that's really useful. And we also have a bunch of visualizations like this one. So where you can see the whole matrix and you can highlight into a specific, like you can look at a specific capability and then look at a specific test and see what's the failure rate, what examples are failing, what examples are passing. So you can get a lot of bang for your buck with this tool. Now you may be thinking, well, this is so simple. There's no way that you're going to find bugs. People are already doing this left and right. So let's see. Let's just test some state-of-the-art models. And we tested 3 tasks. The first one was sentiment analysis, as I talked about before. And here we were testing, pretending that we're doing sentiment analysis on Twitter. And the reason we chose this task is because we were testing commercial models from Google, Microsoft, and Amazon. And all of them use Twitter as a use case. So all of them should kind of work on Twitter. It's not going to be out of domain for them. We also tested some research models, Bert and Roberta, trained on movie reviews. So these are not trained on sentiment analysis on Twitter, but we still tested them just to see how they behaved. Here I have a full checklist matrix with the 10 capabilities, and this is just to guide us as to where our tests are. I'm just going to show a few examples. We have many more in the paper. So if we're testing the vocabulary of sentiment analysis, and we want to use an invariance test, here's one that we could do. We're replacing neutral words with other neutral words. So we get tweets like this. The nightmare continues becomes our nightmare continues. Should I be concerned that becomes should I be concerned when? So it's not changing the sentiment at all, and we see how often our predictions changing. And here are failure rates for different models. You can see that in particular Google and Amazon in this one don't do as well. So if you change completely neutral words with other ones, you're changing predictions 16% of the time or 12% of the time. Now, if we're doing a direction expectation test, I had this particular one before where I'm adding very negative sentences to the end and expecting sentiment not to go up. And it goes up quite a bit for a couple of models, Google and Roberta. It goes up with a margin like a third of the time. So that's a concern. In terms of robustness, since this is Twitter, we thought, okay, this model should be robust to adding random URLs or @ signs. So that's what we did. We took existing examples and added random, completely random, not adversarial URLs or @ signs, and expected prediction to remain invariant. And for all models, basically, it was not invariant. So these models are not robust. If you look at Amazon, for example, in this case, 25% of predictions change if you do this, and change with a margin. It's not just examples that are in the boundary. We tested temporal awareness by doing a temporal change, and this is a little harder. So things like, I used to hate this airline, although now I like it. The model has to understand the temporal dimension. And for all of these, you should think it's not just one example, it's 500 examples like this one. I'm just showing one so you can get a feel for it. Failure rate for this is in the 40s for all the commercial models, so they're not doing this kind of temporal reasoning. We tested very simple negation, like this wasn't a lousy customer service, and we're expecting that the prediction is not negative, so positive or neutral. And failure rate is super high. Like it's very surprising. This is very basic negation. You'd expect commercial models at least to be able to handle this. And the failure rate is quite high for all of them. In particular, Google, 54% for examples like this. And if you make it a little harder, like ending with negation, I thought this would be awful, but it wasn't, and so on, then the failure rate is 100% for almost all commercial models, and even BERT is not doing very well here. Roberta is doing well in terms of failure rate. So obviously there's a lot that these models are not doing. Finally, we did a simple test with SRL where we're doing Q&A. Do I think this is bad? No, or yes, and the expected thing. And again, failure rate is super high. So these models are not really understanding text and understanding the sentiment, at least in this little more complicated cases. Now this is sentiment. Another task we did was Quora question pair, where the goal is to detect duplicate questions. So you have a couple of questions on Quora. You want to know if they should point to the same answer, so detecting if they're duplicates. And in this case, we only tested research models because we don't have access to commercial models. And both research models are supposed to have superhuman performance. They're supposed to be better than humans at identifying questions who are duplicates of one another. So let's see, here's some tests. Testing the vocabulary. The simplest thing we could think of was adding modifiers. So is Patrick Thomas a teacher? Is Patrick Thomas an accredited teacher? And adding the modifier there makes it such that they're not duplicates. They're different questions, obviously. Failure rate is 78% for both Bert and Roberta. And examples like this. NER, we did a directional expectation test where we changed the name in only one of the questions. So you have two questions about the same person, in this case, Donald Trump. And in one of them, we changed Donald Trump to a random name, John Green. And expect, look, if the questions were duplicates before and you changed a named entity like that, it's not going to be a duplicate anymore. But Bert and Roberta still predict there's a duplicate about a third of the time. We also did a different one where we're doing the opposite thing. We're keeping the entities and filling in with gibberish, not gibberish, with things that make sense. So you have something like, will it be difficult to get a US visa if Donald Trump gets elected? Turns into, will the US accept Donald Trump? So clearly those are not duplicates. And the model will only predict duplicate if it's relying on shortcuts. And in this case, Bert and Roberta do it a third of the time again. So clearly not superhuman performance in these examples. We tried very basic temporal awareness, like before is not the same as after. Is it unhealthy to eat before is different than after 10 p.m.? And Bert fails about 98% of the time, Robert about a third. We did simple active and passive swap. So for example, does Anna love Benjamin? Is Benjamin loved by Anna? Those are supposed to be the same thing. Obviously, we just changed active to passive. And Bert and Roberta fail quite a bit. And no human would fail these tests, basically. We also did the opposite where it's different semantics. We keep the order. Does Anna love Benjamin? Is Anna loved by Benjamin? Those are different. We change who the actor is. And Bert and Roberta fail 100%. So even though performance on a benchmark is really good, it's clear that there's a lot of room for growth here. We shouldn't be saying that these models are beating humans just yet. Finally, we did squad, which is question answering, given a paragraph and a question, give an answer. And we tested a research model, BERT large, and again, it's supposed to be better than humans at this task, but we'll see that it has significant bugs as well. So we did very simple taxonomy tests, basic properties, like there's a large pink bed. What size is the bed? We expect model to know that size refers to large, and we also ask what color is the bed, refers to pink, and so on. And BERT fails 82% of the time. So in this case, it says, what size is the bed? Pink. And we tried simple antonyms, like someone is more optimistic, who's more pessimistic, and different words. This is just one example. We have 500 of those. Failure rate is 100% for this, so it doesn't get antonyms at all. We did temporal awareness, again, before and after, last and first. Very simple examples, and failure rate is 83%, so it does not get before and after. We did simple negation, both in the context and in the question. So if you have a context like Aaron is not a writer, Rebecca is, who is a writer, we expect a system with superhuman reading capabilities to know that Rebecca is the writer here, but BERT fails 2/3 of the time. And if the negation is in the question, it fails 100% of the time. So if you don't have negation in the context but have it in the question, it just can't figure it out. We also did a few fairness tests. This is just one example of it making selective mistakes. So it's just like the negation example before. Person is not a doctor, this other person is. If we constrain it such that the person who is not a doctor is always a man, it still thinks that the man is the doctor 93% of the time. But if we make the man be the, if we change it around, BERT does not make this mistake. So it's 1.2% of the time it predicts the woman as a doctor instead of the man. So it clearly is kind of selective. If we change doctor to secretary, it flips around. It doesn't think the man is a secretary, but it often thinks that the woman is a secretary. So there's something going on in here that's worth investigating. We also had some basic co-reference tests. If you're doing reading comprehension, you have to be able to figure out co-reference. Like Melissa and Antonio are friends. He's a journalist, she's an advisor. You have to be able to figure out that he refers to Antonio and she refers to Melissa, but BERT just cannot do this with these simple examples. Same with former and latter and so on. 100% failure rate here. And finally, we did active, passive things like Christian punched Nicole, who was punched, like clearly Nicole was punched, but Bert thinks Christian was punched against 60% failure rate. So this is just a few examples. We have many more, but the point is we use the same process. We use the same matrix. And we detected very different bugs in different tasks and models, commercial models, research models. So this is useful. And also state-of-the-art models still display many bugs. Like we may think that they're beating humans, but that's more of a function of us not testing them thoroughly than their actual capabilities. And many of these bugs, I think, were unknown before this paper. We haven't seen a discussion of them at least. Now, how hard is it to find this? Is it the case that, well, we literally wrote a paper presenting all of these bugs and this technique and so on? Can other people do it without spending too much time? And the answer is yes. So we have two examples of this. One is a case study. I went to the people at Microsoft who trained the sentiment analysis model that I was testing before and asked them, hey, how do you guys test this? So they actually had a pretty thorough testing regime in place where they had multiple benchmarks. The model was being used by a lot of customers for a while. So they had customer complaints. They had a lot of testing being done. And we thought, let's see if CheckList helps even for a model like this that has been stress tested. So we did a case study with them. They came for a 5-hour session. And we went through CheckList. I didn't tell them about my bugs. They were doing it themselves. And in 5 hours, they found many new bugs. They tested new capabilities, and this is what they said. And old capabilities that they already tested, like negation, they had a benchmark just with negation. With CheckList and our test types, they tested it better and found a variety of bugs. So CheckList is useful. You take a 5-hour session for a mature product, and they still found a lot of bugs that then they went to try to fix. We also did a user study. So the case study was with expert users, people who were training the model, people who had tested it. The user study was with people who are either researchers or engineers or data scientists who had not played with this particular model before. So we're testing BERT on KQP for a couple of hours. And we have 3 conditions. One condition, we just tell people, hey, here's a Jupyter notebook, test the model, create whatever examples you like, use whatever you like. We didn't give them anything else. So take 2 hours and figure out what this model is doing, whether it's working or not. Find bugs, basically. The other 2 conditions, one, we told them what to test. So we gave them the capability list and said, try testing negation, try testing named entities, try testing, etc. And the other one, we gave them tooling, templating, and so on. So the 2 on the right are subsets of checklists. And we measured in 2 hours, how many tests did they come up with? And obviously there's a lot of variation, but when you tell people, here's what, when you give them guidance, they create more tests, basically, many more with checklists. We also measured how many test cases they had per test. And if you're doing it by hand, it's very hard to scale. Without tooling, people just came up with 5 to 7 test cases per test, and that is not enough coverage, basically. And then finally, we measured how many bugs they found. So we had a rating criteria, and they rated themselves, and we had an independent rater. But the point is that with checklists, they found almost 3 times as many bugs as without checklists. And this is really helpful. This is in the same amount of time. And they found the same bugs we did. They found new ones with checklists. Whereas without checklists, they found stuff that was already present in the validation set. So if checklist was really helpful here in this user study, people came up with more tests, more bugs, more coverage, and it was fun. And this is a couple of hours. So these are bugs that were not present in the literature, but most of our subjects were able to find them in a couple of hours. And they also found bugs that we hadn't found, so this is encouraging. So this is it. Here's a summary of what I just presented. And if you take away one thing from this talk, this should be it. We should test NLP models. Let's not just trust accuracy on validation data or test data. Let's go ahead and test them just like we test software. It's not that hard, and it really helps to figure out if they're working or not. So we have suggestions as to how to do this. We borrowed insights from software engineering. So checklist tells you what to test, gives you a list of capabilities, not exhaustive, but still really helpful. We tell you how to test. There's simple examples like unit tests. There's perturbation tests. These are really helpful. And then we give you a bunch of tooling. Like we have Roberto suggestions, visualizations, lexicons, and much more. And you can try it out yourself. This is all open source. I'm actively developing, adding new features, and there's a lot of people already using it, giving good feedback. And also make sure to check out the paper. There's many more fun examples of bugs and obviously a lot more detail as to the principles of what's going on here and etc. But that's all I got. Thank you.